Today's e-lesson is all about how scientists communicate numbers. Chemists aren't the only one to use numbers, but all scientists have to make some decisions when they share their information with other scientists. For example, how many digits do they represent in their measurements? How do they express numbers that are really, really large or really, really small? And what is this idea of information being accurate or precise? Tomorrow, we're going to practice some use of numbers in science, and hopefully you'll become more familiar with these concepts. If the goal of science is to understand our natural world, then it's a fundamental goal of a scientist to communicate their learnings with others. In order to do this, it's desirable to have a standard way to communicate data, so those from other labs, other countries, can understand the work. So how do scientists communicate really, really small and really, really big numbers? That's called scientific notation, and we'll see what that's about in a minute. In addition, scientists need to tell other scientists what type of equipment did they use. Did they use a school ruler that costs about 35 cents? Or do they have access to a laser-guided measurement tool that costs thousands of dollars? Certainly the kind of data you obtain from those two devices is not the same. So scientists have a way to share with other scientists the type of equipment that was used to collect the information. Scientific notation is the accepted way to express really, really large or really, really small numbers. Scientific notation is always written as a number times 10 to some power. And the number needs to be between 1 and 10. The power can be a positive number for really big things like the distances between planets, or the power can be negative and be very small, perhaps the diameter of these cells seen here. The power itself must be an integer, it can't be a decimal. So we can see some examples of scientific notation. 100, when we put that into scientific notation, we move the decimal place 2, so we end up with 1 times 10 to the second. Similarly, some of you may know this as swinging the decimal. So if we swing the decimal 3 places here to get our number between 1 and 10, we would then make that power of 10, 3. We can do a similar concept with small numbers, and you can see here how they take the decimal place and swing it. If we go 1, 2, 3, 4 places to make this number be between 1 and 10, we would end up with 10 to the minus 4 as our power. I have posted a information sheet on Edmodo for you with some specifics of how to do scientific notation on your calculators. Make sure you know how to use your tools. Otherwise, you're going to have to revert to the old swing the decimal method. There's also some interesting tricks of doing math with scientific notation, and we're going to get some practices doing that tomorrow. So if that's something that you don't remember or you were never comfortable with, you might want to look at the PDF file that I attached. So the fact that we can put numbers into scientific notation and sort of remove the zeros brings us to this concept of a significant figure. Significant meaning something that's really important and something that matters. So in science, a significant figure, a sig fig as I sometimes call it, is a number in a measurement that is really important. And it shows the reader what kind of measurement tools that I used. Again, did I use a 35-cent ruler or did I use a multi-million-dollar laser-guided measurement tool? And as a quick understanding for the role of significant figures, let's look at this little coffee example. If I have a coffee cup that I am told holds 200 milliliters of coffee, and I add 1 drop of water to it, what is my new volume? Is it still really close to 200? Or should I really represent it as 200 plus 0.05 milliliters? Certainly that's going to depend on what kind of measurement tool I use. We're going to see in a minute that measurement tools allow us to estimate the actual last digit. So we can read between the lines, so to speak, and say whether or not the piece of string is 2.45 or 2.48 centimeters long. Now, unfortunately, there are some rules that go along with this idea of a significant figure, and I've posted them on a PDF file for your review. We'll practice with those tomorrow, so I want you to take a quick look at that so you understand this idea of what digits count and what digits are insignificant or are only placeholders, and how we do mathematical calculations with significant figures. This is where we get into trouble. We can crunch a number on our calculator and we end up with 9 decimals, but that doesn't mean all of those numbers are significant or actually represent something that was measured. Now that we have an idea of what a significant figure is, one that really means something in the measurement and not just an extra decimal that we carry, I'd like you to try to make some measurements and report the correct number of significant figures. This little figure here gives us a hint that we are limited in the number of digits that we can report. Generally, we're going to estimate in between the smallest gradations on a measurement tool. And what do I mean by gradations? This ruler here only has a single marking on it, where this ruler now breaks those marks into 10, and this ruler breaks each of the individual lines into 10. So I can estimate in between any of the markings. So with that in mind, I'd like you in your notes to try to estimate the volume in this graduated cylinder. A little more tricky to estimate the one here of the actual liquid. And then I'd like you to tell me how long this purple line is. Knowing that I can't draw a straight line, but still try to estimate, using the 3 rulers, the length of that purple line. And we'll talk about your measurements tomorrow to see how many digits we should report to make sure that the reader really understands which of the rulers I'm using. Certainly this ruler is going to give us less information than this ruler. The last thing we need to talk about is this idea of precision versus accuracy. Many students use these terms interchangeably, and they're not actually meaning the exact same thing. Accuracy is how close the measurement is to the true value. So in this example, we can see the 3 arrows are all very close to the center bullseye. So those would be accurate measurements or accurate throws. A precise set of measurements are those that are in close agreement. So here we can see this dart thrower is very precise. Now they're not accurate because they're not landing on the bullseye. In this case, we can see that these measurements or arrow throws are not accurate or precise. An example that might make more sense to you is consider your bathroom scale. If you know that your bathroom scale is off by 5 pounds every time you step on it, you can still use your scale to get good measurements. That would be a precise measurement tool. You could correct for its being off by 5 pounds by subtracting that from your weight. An accurate bathroom scale would show your true weight every time you stepped on it. So clearly we want our tools to be precise and accurate, but we can live with precise measurement tools because we can always correct or calibrate them to allow us to obtain useful information.